Sorry, I just remembered that I needed to record this, so I just started recording it. So what's the relationship between these two compounds here?
They're enantiomers.
They're enantiomers. They are actually diastereomers. Because this chiral center is the same in each case, right? So this chiral center is the same, but this chiral center is different. So the OH group is pointing towards us in each case, but the X is there either pointing towards us or pointing away. So when we had protons that were, when you replaced them with an X and they made the same molecule, we called those homeotopic protons. When we had protons where we replaced one with an X in each case and they made enantiomers, they were called enantiotopic protons. What do you suspect we would call protons like this, which generate two different diastereomers? We call these stereotopic protons. And these protons can have different chemical shifts. So when we were doing our numbering before, I think in the last lecture, we said that this molecule could have 5 different protons. Sorry, let me use my laser here. We said that why is my laser not working? Maybe it's because it's laser. There's my laser. Okay, it's not working on the pen. So we said in the last class that this compound could have a grand total, should have a grand total of 5 different signals. 1, 2, 3, 4 for these guys and 5. But really, these 2 protons can have different chemical shifts. So it's possible that there could be 6 different classifications of 6 different protons in this case. So diastereotopic protons are the exception to, so they can, sometimes they have the same chemical shifts, but sometimes they're different. So that's the one thing to keep in mind. So yeah, I was just looking back at the last lecture and yeah, so this is, there could be 5, but there could be 6. Right. Okay, so that's basically where I wanted to point that out. Now, if we go back to the various things that we should see on a spectra, so we should see the number of signals will tell us the different kinds of protons there are. The second thing would be the location, which is the chemical shift. And this is going to tell us the environment of the electronic environment. Is it in an area of shielding? So is it shielded, like or is it in an area of deshielding? And we had the correlation table, which basically told us, which would give us a hint of where things tended to be. So we'll use our correlation tables to talk about that. The third thing was the intensity of the signal. And if you do the mathematical area under the curve, This would give us basically an integral, and that's going to tell us the number of protons. What am I doing? That make that signal. So I'm going to redraw this little chart way down here. Let's pretend that we've got a chart. Here's our 0 ppm. And let's pretend that we've got a signal here. There's a signal here. There's a signal here. And the integrals are going to be above the line. So let's say that this is like this. This one is like this. And this one is like this. And if our, so the proportion, the size of the integral is going to tell us the number of protons. So let's say our formula had 5 protons. How many does each one of these integrals represent? A, B, and C. So the height of the integral is proportionate to the number of protons that make up that signal. So how many protons make up A, how many make up B, and how many make up C? If there are 5 in the formula.
I would guess 2 for A, 1 for B, 2 for C.
Oh, what happened to? Yes, that's exactly correct. So often when you do run the integral, there'll be a number associated with them. But if there's ever a case where there isn't, then you basically need to make an educated sort of guess by just the heights of them to determine which one is which. So if we had another chart and there was a signal here and there was a signal here, and the integrals, and there was 6 protons, and let's see here, I need and this integral here was like this, and the 2 integrals were basically the same height. That would tell us that the 2 signals, there would be 3 here, 3 here. So yeah, this would be 2H, 1H, 2H. And often let's stop doing that. Often this part's overlooked by people. So just keep in mind that the peak heights are, they're basically proportional to the amount of protons there are. And if there's only 2 signals and one's twice as big as the other, or if they're equal, same height, then whatever the formula is, it basically you have to make it sort of fit so it works right. The exception is often if you have a proton on a heteroatom like OH, because those signals tend to be very broad, these ones sometimes don't integrate very well, so you might not actually see them. So I'll show you an example of that a bit later on. So yeah, those were the integrals. And then the last thing, which we never got to, the fourth and final part to all of this, was part 4, number 4, is that often the signals are split. So they don't always appear as a wonderful little straight line. They often appear as 2 lines of equal height, or 3 lines. So the ratio of the peak heights would be 1 to 1. Here, the ratio would be 1 to 2 to 1, or sometimes they appear as what we would call a quartet, 1 to 3 to 3 to 1. So they're often split into, the signals are often split. So we call this a doublet. We call this a triplet. We call this a quartet. And this little guy would be a singlet. And what this tells us, the splitting of the signals, this tells us about protons on nearby carbons. So we're going to get into that today, I guess. What am I doing? Okay. So, right, so let's pretend that we've got a proton and it's on a carbon. And the neat thing is that the protons can sense carbons, the protons can sense other protons on carbons that are nearby. Or even in the case of what we were just talking about, sometimes if you've got diastereotopic protons, they will sense the protons on the carbon which they're bonded to themselves. And so this is basically called splitting. And this interaction is what we call spin coupling. And we'll see what we mean by that in a second. And so this spin coupling it's basically transmitted through covalent bonds. And it's measured in what we call, it's measured in hertz. And it's got a special name called a coupling constant. So because it's transmitted through sigma bonds, depending upon how close, like how many bonds there are between where the protons are, like, so in this case with the black line, there's 1, 2, 3 bonds. So that's got a specific type of name to it. And in the case with this blue line here, it's transmitted through 2 bonds, so it's got a completely different name. So the measurement of this interaction is called the coupling constant, and it's got a symbol J, and it's measured, as I said, it's measured in hertz. So so some people call that the like a J value coupling constant. And so what tends to happen is that for, oops, there's a question somewhere. I must have missed it. What happens here is that typically the fewer the number of the bonds, the higher the coupling constant. So we'll talk about this in a second. So let's just talk about the different types of coupling. we've got what we call geminal coupling. Let me get this in black here. Geminal. So if we had a, yeah, just our friends here, which we talked about earlier. These two protons are not equivalent, so they will sense, because they're diastereotopic protons, they will sense one another and they will couple with one another. So these two diastereotopic protons we had before, this would be a geminal coupling. So sometimes this is called like J2. This little 2 up at the top describes the number of bonds it's passing through. So so geminal couplings, the J values tend to be greater than 10 hertz for sp3 hybridized carbons. For sp2 hybridized carbons, it's lower. So a geminal coupling for an sp2 hybridized carbon would be XY, be something like these two protons sensing one another because they are not equivalent because of the different substituents on this double bond. So in those cases, these ones are kind of small. They tend to be less than 4 hertz. So with the sp2 hybridized carbon, this coupling is less, but with the sp3, this geminal coupling is quite large. The most common type of coupling that we see, and we talk about the most in NMR, is vicinal coupling. Did I spell it right? So this is through 3 bonds. So this would be a 3J. So the most common example is what we had before. So stop it. The J values here tend to be between 6 and 8 hertz. So in our molecule at the start, if we have H, these 3, I guess I'm going to draw this H. Actually, let's erase these 3 because we don't need them for the time being. So if we're talking about our 2 little protons, our diastereotopic protons here, they can couple, this guy can also couple with this proton way over here. And this is a 1, 2, 3 bond vicinal coupling. This proton here would also couple with, and that would be a 3 bond vicinal coupling as well. So this little 2-butanol could have quite a complex little structure, NMR, just because these protons are diastereotopic and they would couple with this proton plus the ones over here, which is going to complicate things even more. Some other vicinal couplings that we could see would be if you had between here and here, this is 3 bonds, 1, 2, 3. These are around 6 hertz. The vicinal couplings that are quite large, though, are on double bonds. And this is one of the ways that you can actually determine the double bond geometry. So in infrared, we use the fingerprint region to look at the out of plane bends. But with proton NMR, trans couplings tend to be quite large, between 12 and 18 hertz, often around 15. And cis couplings, when they couple with one another, they tend to be lower, like 6 to 12, and average around 10. So you can usually, the high end of the cis is the low end of the trans. So it's often you can easily distinguish between the two of them. So these are still 3-bond couplings. And then there's such a thing as 4 and 5-bond couplings, long-range couplings. But for right now, we're not gonna talk about that. Now, why do these peaks? Why do they split? Why do they split? And if they do, why do they appear as like a doublet or a triplet or a quartet? And the ratio is 1 to 1, 1 to 2 to 1, 1 to 3 to 3 to 1. Okay, so let's pretend that you are a proton. So this is you. And you have got a proton over here on the carbon next to you. Okay, now, what was when you were, so when, if we think back to the way that the whole NMR process works, you're a proton, you've got a nuclear spin quantum number of I equals 1/2. So when you're not in a magnetic field, you're basically randomly pointing in any direction you want to be. But then you're put in a magnetic field. What happens when you are placed in that magnetic field, B0?
The proton's spin aligns with the field.
Right, so some of the protons will align with the field. They will be the 1/2 protons, and some other protons are opposed, right? So they'll be the -1/2. And remember, there's an energy difference between the two, so -1/2 +1/2. Okay, so this is you, and you're placed in the magnetic field, and you've got a neighbor. There's basically 2 different scenarios that are going to transpire here. We're going to keep you constant. But in one reality, this proton here is aligned with the field, so it's at 1/2. In the parallel reality, the proton next to you is opposed to the field, so it's at -1/2. Okay, so now what's going to happen? Okay, so this is still you. You are living in 2 different realities here. So in one reality, your neighbor is aligned with the magnetic field, and in one reality, your neighboring proton is opposed to the magnetic field. Okay, so now the NMR technician is they're using a continuous wave spectrometer, and they are sweeping the frequencies, and they're causing all of the protons to resonate, right? Okay, so we'll call this reality A, and we'll call this reality B. So remember, you are going, you're going to resonate, and it's going to depend upon how shielded you are or de-shielded you are with respect to the applied field, right? So proton, your neighboring proton here, which is aligned with the fields. So you're typically, if you didn't have any neighbors, you would resonate at this chemical shift here. This little delta symbol is when you've got chemical shift. It's got this symbol, this, right? So this was, if you had no neighbors, you would resonate there. Do you think that you are going to resonate at a lower frequency or at a higher frequency when your neighboring proton is aligned with the field? So your neighbor is basically where they, if they're opposed to the field or if they're aligned with the field, they're going to cause you to resonate at slightly different frequencies. So in the case of when you're aligned with the field, you're always going to resonate at a chemical shift slightly closer to, at a lower, with less energy, because now this is aligned with the field and you're being de-shielded. Whereas when you've got a neighbor who is opposed to the field, they're going to cause you to resonate at a frequency that is higher in energy because they are shielding you from the applied field B0. So this difference between these two peaks here, this is the J value, and it's measured in hertz. And so because in this reality where you're this proton and you've got one neighbor, there are two possible scenarios: the spin up and the spin down. If you are this proton here again, and you've got two neighbors, let's pretend that there's free rotation around this bond, so both of these protons are equivalent. Now there's a grand total of 4 different scenarios from which these protons can be, how they are aligned with the field, right? So we're going to keep U constant. And let's write these 4 scenarios here. Stop it. So I'm going to represent the possibilities that the protons can have by just drawing little arrows, right? So there's one scenario in which both, if this is the applied field here, E0, there's one scenario where both protons are aligned with the applied field. There's one scenario where both protons are opposed to the applied field. And there's 2 scenarios where one's aligned, one's opposed, one's opposed, one's aligned. So when you have 2 protons next door to you, you're going to be split into 3 different signals. And so you would look like this. So you would normally resonate right here. And when, let's put another color, red. In one scenario where you're resonating, if this was where you'd normally resonate, there's one scenario where it requires less energy because the 2 neighboring protons are de-shielding you. There's one scenario where you are resonating, oops, because you're shielded, because they're both opposing the field way over here. And then there's two scenarios in the middle where you resonate exactly where you were supposed to. And so the signal ratio is 1 to 2 to 1. So this peak would be 1, this peak would be 1, this peak would be 2, because there's two possible scenarios there. So in this first example where we had one proton next door to you, so you had one neighbor, you were split into two signals. So if this equals n plus 1. So there's basically a rule, the n plus 1 rule for first order spectra. It's actually technically, the rule is, let me write it down here. It's actually 2i n plus 1 rule. But proton I equals 1/2. So 2 times a half is 1. So the rule basically comes down to the n plus 1 rule. So when n is the protons next door, so if you've got one proton next door, when n equals 1, you are going to be a n plus, so 1 plus 1 equals 2. You are going to be a doublet. When you've got two protons next door, so this case right here, 2 plus 1 equals 3, which is a triplet, which is what we've got here. And if you had n equals 3, 3 plus 1 equals 4, you would be a quartet. And the ratio for the quartet is 1 to 3 to 3 to 1. So there's one example, so one proton, there's 3 protons all aligned. There's one chance where all 3 protons are opposed. And then there's one scenario where there's 2 aligned and 1 opposed. And then there's 3 possible scenarios where 2 are opposed and 1 is aligned. And so the chemical shift for a quartet is basically right in the middle of the 2 center. That's where you would normally be if you didn't have any neighbors. And there's a thing called Pascal's triangle, which basically tells you how to, I can't remember when I learned Pascal's triangle. The way you make it is by, so these, if you add, like the sides are basically, it's always 1 going down, but if you add these 2 together, that equals 2. If you add these 2 together, that equals 3. If you add these, 2 plus 1 is 3. So 1 plus 3 equals 4. 3 plus 3 equals 6. 3 plus 1 equals 4. So this would be the doublet. This would be the triplet, quartet, quintet. Below that's the sextet. And you can get and so the peak heights for each thing will be this thing. So the neighbors here would be 1, neighbors would be 2, neighbors would be 3, neighbors would be 4, neighbors would be 5. How do you get 5 neighbors? Well, we'll see about that in a second. So the origins of this basically arise out of the fact that protons nearby can either be aligned with the field or opposed to the field, and you as a proton can sense it, and you will, in certain scenarios, you'll be shielded, in other scenarios, you'll be de-shielded, and that causes you to to resonate at a slightly different chemical shift. And so the value between these two peaks is the coupling constant. So in this scenario, we fixed U as proton here or here, but there's another world in which the proton here is sensing U, because you could be aligned with the field and you could be opposed to the field as well, right? So there'd be another proton on this chart, which would also be split into a doublet. And this coupling constant between the two, this is going to be the same. So if this is 7 hertz here, then this coupling constant here between these two peaks will also be 7 hertz. So you will share that coupling constant with the neighbor which you're coupling with. So it's one of the, it's actually used to determine, like some protons are coupled by number of different other protons, so you can actually link, okay, this one's coupled to this one at 5 and this one's coupled to this one at 4 or whatever it might happen to be. So let me see here. Let's do a little, is there a question? It is 12:30. Oh yeah, sorry, I went over time. Okay, so what we'll do on Thursday is we're going to do a bunch of practice spectra. Yeah, that's what I might give you a little top hat quiz on a couple of things just to see if everyone's got the concepts down. It won't count for anything except for participation, but we'll just do a bunch of practice spectra so everyone gets the hang of it. Sorry for going late. Were there any questions?
I have a quick question.
Sure.
Do you have other recordings for mass spec? On top at the only one of the recordings was posted.
Oh, which one's missing?
Oh, for mass spec, there's only one, like total.
Okay, there was a major screw up on one of the days where I think a recording was missing because it got butchered. I don't know if it was in this class or organic. Are we missing any in organic? I'll take a look because maybe it's just it's been processed and I just haven't posted it there. But I'll take a look. But there was one day where something bad happened and like today, I almost forgot. I started recording after 5 minutes. So if someone wants to remind me at the start of each class to press record, that would be super. But I'll look for it.
Okay, sounds good. Thank you.
Okay. All right. See you, everybody. I will end this.